Hello there. So right now we're going to talk about point slope form. So what's point slope form? Let's first of all think of this in terms of transformations. We've seen a couple of transformations. For example, we start with the parent function y equals x squared. And y equals x squared looks like that. Now here, the vertex of this guy, the vertex goes to the point 0, comma 0. And let's give this thing a name. Let's call this vertex Bob. Okay, now let's say we want Bob to be somewhere else. Let's make a new point here. We're going to call this point 2, comma 0. And I'm going to call this one new Bob. Okay, so new Bob is there. Now if I want to move this to the right, then I make my new equation. And the new equation is going to be x minus 2 squared. Okay, and now you can see here the vertex goes through the point new Bob. Now let's say new Bob, I want to make new Bob 2, comma 1. Then here in this thing, I'm going to raise that up 1. So I have Bob and I have new Bob. And I've transformed my quadratic and I've moved it to the right 2 and up 1. Now the same thing happens here if this was an absolute value function, right? Let me go ahead and hide all of these. So absolute value function is going to be, let's see, absolute value of x. And it goes through the point Bob. And if I want this to go to new Bob, then I'm going to write this absolute value function as x minus 1. Actually, sorry, I meant minus 2 plus 1. Okay, so I have my original function, my original absolute value function. It goes through Bob, and then the new one goes through new Bob, and then same thing with my quadratic. Let me go through this. So original quadratic that goes through, so we got Bob and new Bob. Now I'm going to do something kind of different here. Let's say I have a line. This line right here is y equals x. Now I want to make another line that goes through the point new Bob. What I'm going to do here is I'm going to do y equals parentheses, same idea here, x minus 2 plus 1. And you can see that new line, it went through Bob and it goes through new Bob. Okay, so let's say I want to have a line. Line is going to go through the point negative 1, comma 2. And let's call this point newer Bob. Oh, never Bob. Okay, we'll go with never Bob. Okay, so we got Bob, new Bob, and never Bob. So we want a line that goes through never Bob. So if I want a line that goes through never Bob, we're going to do y equals parentheses x plus 1. Why am I doing plus 1? It's because this is negative 1. Okay, so x plus 1. So let me go back. So x plus 1, close that parentheses, and now we're going to do plus 2. Okay, so now I have a line. It goes through never Bob, and I can even change the slope here, right? 2 or 23 or any slope I want. Okay, so you have a line that goes through Bob, a line that goes through new Bob, and a line that goes through never Bob. Okay, so let me just make this now formal and write this thing out. This is called point slope form. And it goes like this. Y equals m x minus h plus k. So we're used to seeing lines in this form. This is called just normal slope-intercept form. Y equals mx plus b. Now this is super useful if you have a graph and you know the y-intercept. Let's say the y-intercept is 7, the slope is 2, then you just write y equals 2x plus 7. But sometimes you might be given this kind of situation. You see a line and it goes through that point, and this point is 1 comma 5, and it just kind of goes on and on forever, but you can't really see the y-intercept. Let's say the slope here is a half. So let's write this out. Y equals, slope is a half, 1/2 x minus 1 plus 5. Now where does that minus 1 come from? We're going to flip that sign right there, and the 5 comes like that. Okay, so let me do this one. All right, and let's say we know for sure it goes to the point -1 comma 8. And the slope, if I just picked a little arbitrary section of it here, and it went down by 1 and over 3. Slope, remember, slope is rise over run. So the slope here is -1, 3. So when we write this out in slope-intercept form, y equals m, slope is -1/3, x minus -1 plus 8. So equals -1/3 x plus 1 plus 8. And we could simplify this further, but for the purposes of this unit, we can't actually just leave it like this. The computer will accept it in this unsimplified form. Now let's say we had another point here, 2 comma 6. Which point do we use, right? Does it matter if we choose -1 comma 8 or 2 comma 6? And it actually won't matter what point we use. It will eventually, if you were to simplify it, simplify down to the same form. Okay, so when would we ever use something like this? We're going to use it in this type of question. So let's draw a line. Something like this. Let's go all the way up here. And then, okay. So let me draw some points here. Let's make this -1, 0, 1, 2, 3, 4. And let's have this be 1, 2, 3, 4. And yeah, so it's not drawn here, obviously, very nicely. But we'll just go with this. So the question that we need to do on this is to define the different bits of this function. So first of all, let's define this line right here. So this line, it's a flat line. Now as I move my cursor along this line, as I trace this line, what stays the same? Is my x value staying the same or my y value? As I move along this, my x value moves from -3 to -1, but my y value is staying constant at -2. So this is the line, f of x equals, and it's going to be -2. As long as x is from -3 to -1. Now it includes -1, so we put a little line under there. It doesn't include -3, it's an open circle. All right, so we're defining this function as 3 different sub-functions. Okay, this one right here, this is a quadratic, and it doesn't look very beautiful, but let's go with x squared. Okay, this is y equals x squared. How do I know it's y equals x squared? Because I have the point -1 comma 0. I have 0 comma 0. I have this point 1 comma 1. And I have the point 2 comma 4. So it looks like that x squared function. Now that applies when x is from -1 all the way up to when x is equal or less than 2. Okay, so from -1, not including -1, all the way up until positive 2. Okay, now the last one, we have this line. So how am I going to define this line? Now, here's why point, what do I call it? Slope intercept form or slope point form. This is why that new form I was talking about is so important, because I can't really see the y-intercept here. So we're going to use this point. Let's do this in a different color. This point right here is 2, 2. And if I'm looking at the slope here, I'm going down by, what is this? It's like 0.5. So I'm going down by, from, let's see, this point right here is 4, 1/2, right? This looks like kind of 1/2. Okay, so I'm going down by 1 1/2. And I'm going over by 2. So the slope of that line is negative 1.5 over 2, which does make it a nicer fraction. That's the same thing as negative 3/4. So when I write this out, we're going to do negative 3/4 x minus 2 plus 2. And this is when x is from 1, or actually when x is from 2, right? X is from 2 all the way to 4, including that 4. Okay, hopefully that made sense. Let's do one other example here one more time. Okay, let's just focus now on that line. 1, 2, 3. 1, 2. And let's say I've got this point, and we're going to go all the way to that one. Okay, so this point right here is 1, 1. This point right here is 3, 2. So first of all, let's find the slope. The slope is rise over run. Between these 2 points, how much do I rise? This is 1. This is 2. So I rise from 1 to 2, so I rise 1. And I run from 1 to 3. So this is 2. So my slope is 1/2. I go up 1 over 2, up 1 over 2. So now we write this as y equals 1/2 x minus 1 plus 1. Or I could write this as y equals 1/2 x minus 3 plus 2. Either one of those examples are acceptable. If you were to go ahead and distribute that 1/2 into those and simplify, you would work that out to be the same answer for both. Okay, that's it.